All right. So welcome back. Now we're gonna start the panel. Let me just check that all the panelists are back from the break. I see Paul. I see Alan. Sudhanva is there as well. Charles, are you there? I can see you in. Yeah. Here is Charles.
Down
as well.
here.
Yeah. Cool. All right. So let's start. So welcome back, everybody. So now we're gonna have 45 minutes open discussion. So these are the four panelists. Paul Carpenter, he already delivered the keynote. Alan Cantle, he's the CEO of Nala's Way and technical director of the Open CAPI Consortium. Then we have Sudhanva Gurumurthy from IMD and Charles Jones from IBM Research. So the panel is organized as follows. So I will give you 1 minute for just warming up and telling the audience who you are, a little bit of your background. And then we have 4 questions prepared, and we're going to spend around 10 minutes on each question. So we should be able to close to the 45 minutes or so. So, Paul, we'll start with you. A very brief introduction of yourself.
Okay, do you hear me again?
Yeah. Loud and clear.
Okay, well, I'm not quite sure what to say because I've already spoken. I'm Paul Carpenter. Yeah. I'm senior researcher at Barcelona Supercomputing Center, doing research on a number of things, including disaggregated memory, also quite a focus on programming models, so variants of OpenMP. Is that enough?
Yeah, perfect. Alan?
Hi, everybody. I'm Alan Cantle. I'm a hardware double E by training, self-taught computer architecture over the years, with a specialty in FPGA compute acceleration has been pretty much my career, heavily getting involved in memory over the years as well. And I currently am the Open CAPI Consortium technical director, with a heavy focus on the open memory interface, serializing the local near memory and also shared memory approaches as well for these composable systems.
Thank you. Sudhanva, you're next.
Yeah, hi folks. My name is Sudhanva Gurumurthy. I'm a principal engineer leading advanced development in resilience. I'm a RAS architect at AMD. So my sort of work recently in terms of composable systems is I contributed to a bunch of resilience things, which are now part of the CXL 2.0 specifications. I've been playing in the CXL space for some time and especially focused on memory. I also work with other standards bodies. So I've been working with JEDEC, so HBM3's ECC architecture is again something I worked on. And before sort of this more advanced development role, I was in industry research, where I worked with Alia, in fact, and Sergey on how do you manage tiered memory systems enabled by things like CXL. And prior to that, I'm an academic, was a university professor before I joined industry about a decade ago.
Thank you, Sudhanva. And Charles, your last.
Hi, Charlie Johns. I've been with IBM for like 38 years with a broad background. I was one of the original architects on CAPI, the predecessor to Open CAPI. I'm currently working on composable system architectures with IBM Research.
Okay, thanks a lot. So let's start with the first warm-up questions. So we have seen that there are now a number of commercial products that enable systems composability to different extents, like Liquid, Gig.io. Now we also have this fungible computing. Now that you have products, what do you think are the remaining blockers to mainstream, and if you want, even at scale adoption of this technology? I will throw the question to one of you so that we avoid who's taking it. Charlie, you want to take this one? You want to start with it?
Sure. I think one of the biggest issues I see is security. Today, a lot of the security is people are moving toward systems that are bare metal, where they don't want anybody else on the system. This is for more confidential computing. So we really need a means for authentication, attestation, encryption, integrity protection for communication between the disaggregated resources as well. So I think that's one of the major issues. Scale is going to be another one where we have today our switches are kind of limited to around 100 lanes. So it's going to limit the scale of our composability. I was very encouraged to see that memory disaggregation need to compose very wide to get the benefits. But that, I'm not sure that applies to all cloud workloads. So that's something I'd like to investigate. I think another area is packaging. Today, our systems are packaged as systems with the I/O integrated in it, the memory, the networking, and your accelerators are all in one chassis. So we need a standard for breaking these things apart and putting them into modular packaging. I think there was a lot of work on dynamic addition and removal of GPUs. I was interested to hear that. But I think we need to get this more driven by the scheduler as opposed to an administrator setting up the systems. I think QoS was also something that was raised during the talks. That's something that we need to look at, reliability as well as the latency. Latency is a much harder, but that higher radix switch will help with that latency reduction.
Even perhaps even software in general, right, will need to be at various levels. Software, the operating systems, software distributed system runtimes, like everything today lives with the idea of hardware is limited within a single box, right?
Correct.
So
with composability, you're essentially making a system look like today's systems, right? By attaching devices and memory to that system. So it should look fairly, with the exception of the NUMA. So I think we will need applications to become more NUMA aware than they are today as well.
Yeah, exactly because especially at scale, a NUMA-like effect is gonna be much more. It's gonna be affecting applications much more, right, than the NUMA effect that we have today within one box. So that's a pretty important part as well. And you have the feeling some of these issues like the security are being addressed already in some of the new standards that are
security
targeting composability?
Security is being addressed. There's a lot of standards coming up, and you see this in CXL as well as PCIe. But are people going to trust that? Where in confidential computing, they really just want that air gap, nobody else running on the system, no possibility for people looking at your memory. But with a shared fabric, are people going to trust that security? So we have some work to do there, I believe, in the industry to prove that out.
Yeah, exactly. Not only the fabric, also device passing dynamically from one customer to the other. Who is ensuring the device is probably getting wiped and reset? Should I trust the infrastructure, the fabric manager?
Right. And that's going to be true for both accelerators as well as memory. Memory is going to have an easier time because it will be most likely will be encrypted if you're interested in protecting your memory. So even though if the memory were to leak over, the next user wouldn't be able to interpret the memory.
Yeah, right. Cool. I'm asking the question to one of you, but if the others want to chime in, okay, it's not just in interrogation one-to-one. So if the others have comments, just jump in. in the discussion.
Yeah, I'll add to what Charlie was saying, right? So one of the other things is that these are all technical issues to look at. The other thing really is that you need a kind of an ecosystem to grow out of this. And this is one of the values of standardization, is that you could actually have multiple devices for which is needed for composability, right? From compute to accelerators to memory devices, networking devices, and so on. And I think the existing systems are good, but I think a lot of these issues get worked out when you have many players, which represent a pretty wide swath of systems being used and deployed, right? So I think that's one of the reasons why standards bodies are a good way to drive some of these things. The other thing also, some of the things I hear is also applications, right? So at least in the research literature, there's been, I would say, tiered memory systems and things like this have been studied for more than a decade, like well more than a decade, right? I remember papers at ISCA 2009. I think there were 3 papers on using non-volatile memory to create tiered memory systems and managing it, right? And we are in 2022 right now, and I think they're still going on. I think some of those killer apps which are large enough and I would say high value enough for large swaths of industry to get together and work on is starting to happen more, but I would say it's going to take some more effort to drive towards some of the system visions which have which the research community at least has looked at for quite some time, right?
Actually, tiering is something that is like coming back these days, because there are patches that are being worked on for the Linux kernel for handling tiered memory system that is not only like cache and regular memory. So for some reason it came back to life, and most probably is not only PMEM, but it's also the upcoming, people are expecting to have CXL, par memory, and so on and so forth. So probably this came back to life and revamped interest, and maybe with real use cases.
I think the latency is one that I've got written down. It was interesting in the talks today, you've got some where actually the latency's improved, and I guess what you're doing is you're going across the PCI fabric, getting rid of the network fabric, so you can sort of see where there's been some potential latency gains. But that is a concern that I see is as you go to these composable systems, you'll have like 128 PCI lanes on a processor today, so you don't need to go for a switch when you're actually hyper-converged in the one box. By adding these composable fabrics like liquids, etc., then obviously you are intentionally putting these additional switches in. So latency does become a big question. I think in all the demonstrations we've seen, the commercial ones anyway, that was why I asked the question, memory is not part of the composability picture right now. It's all the GPUs, accelerators, SSDs, and obviously I see the partitioning with an accelerator is you move compute to an accelerator because it's good at a particular algorithmic function. But what I've seen in the research we've done over the years with the FPGAs, etc., as accelerators, was often you might say, well, this is going to run really well on the FPGA, but not very well on the CPU. But you have a terrible partitioning point because you have so much bandwidth. And it was synthetic aperture radar with FFTs was the application we actually did with Intel once. And essentially, we could partition at a different point and reduce the bandwidth, the communication bandwidth, by a factor of 10 or more, I think it was. And the FPGA was okay at it. It didn't really accelerate that particular piece, but it was better to put the code on the FPGA to minimize the communication. And I think the intelligence of people writing the code, and whether you can do this automatically, of you partition at minimal communication is an interesting point. So these things, the composability of the memory and the latency impact of composing memory, I think is the biggest topic. I agree with everything Charlie said, but the particular one is hardware architecture, we are so infused with a classic IBM PC. You know, the server of today still looks pretty much the IBM PC of 1980. and when you think about it from a composability perspective, we need to break this modularity down so that the composability, and I don't think the memory, you know, I think some of these memory architectures, this pure pooling approach, from a memory perspective, we need to bring energy-centric computing into this picture, because I don't think we realize how much power we burn when we move the memory at the top of the rack and the computer at the bottom of the rack. It's further away. Distance equals power, as well as latency, and sometimes more power than latency. So we need to get energy-centric computing squarely in the research here, guys. And that's something that I've been just doing recently. Some of my presentations coming forward will focus on the energy side of this composability.
Okay. I must admit, I don't really have anything extra to say, because the things I had written down and things that I said earlier in my talk, I can repeat what have already been said. So the whole software stack, I think, needs a huge amount of work. And also, at least in HPC, there's a real need for some kind of standardization. So it doesn't necessarily have to be through a standards body, but there needs to be some consolidation onto a small number of approaches because of the complexity of changing the application. Then the performance overheads, or the latency was also mentioned, has to be really low, has to also be very well understood and trusted to be low, of course, because it's so important in performance critical domain like HPC. So I felt I needed to make my point, but I don't have anything.
Yeah, especially for HPC, the latency and performance issue is going to be critical, right? Because yes. I mean, in HPC, people don't trust already VMs or containers.
Exactly, that's a good point. They
might be losing something.
Mm-hmm.
Let alone if we add a couple hundred nanoseconds to the memory access latency, and we saw it already. With Archit's paper, where it shows that applications like Redis, where there is a lot of networking involved, are not really impacted. But graph traversal, which is probably similar to an HPC workload, instead was killed. So yeah,
factor of 2000 or so.
Exactly, it's like dead. So
that's one reason why I think you got to have local memory to the CPU. You can't have all your memory disaggregated, right? So there has to be local memory as well as pooled memory to meet those ultra high memory demands, right?
Yeah, absolutely.
Yeah, and probably that's exactly the reason why the tiering is back into the picture, right? People are trying to transparently use the local memory for coping with this increased latency. So
yeah, now I love the word memory tiering. We use it so in the industry, we've got this lovely diamond diagram. If you look at the way we do memory tiering, we should call it memory forking. It's not memory tiering. We want to introduce memory tiering with shared memory ports, but today it's memory forking, let's face it.
And it's, I mean, we've done a lot of research. A colleague of mine has done a lot of research at BSc in making use of multiple kinds of memory, so Optane and DDR and so on, and it's very, very difficult to do it efficiently. I think he's got a very good approach that actually works after a lot of research, because they are kind of treating it as a cache leaves a lot of opportunities for improvement.
It'd be nice to turn cache on and off, let the application make a decision of you manage it at the application level, or you have hardware caching. You know, there's benefits to both depending on the application needs.
Yeah, or in the runtime something. So our approach was, because changing the application is not easy, right? But some kind of layer.
Yeah, there's the layering. I think what we really want with memory tiering is we want to have a graceful increase in latency and power, because latency and power are essentially the same a lot of time. And so as you reach deeper into your slower tiers of memory, you just reach through the same port. That's what we want. That's where we need to think of a memory-centric architecture. You put the memory. If we had a memory with a low latency, low power port to the processor, so you've got that piece of memory is local to the processor, and then they've got another port on it, which is a fabric port, say CXL, and that goes to everybody else. Then when this processor wishes to share its memory, because it doesn't need it, it's sharing it through the fabric port, and it's not losing any bandwidth to what it's keeping for itself. And so this is where memory tiering should be true memory tiering, where you've got a couple of ports, a fast port and a slow port, and you've got multiple levels of that. But at the moment, we have our local memory, and so there's a port for that. We have our NUMA memory to a neighboring processor with their own SMP connections, and then we have our PCIe memory, and then we have our Ethernet memory, RDMA. And so it's forked. It's 4 forks is what we've got. We need to make it one port. A processor, a bit like all memory, has only one memory. It's all DDR today. Really, what we want is processors to just have one port. All processors, all accelerators talk one language. They talk memory. That is their language. When you software guys, all you talk to is memory ports, and somehow it squirts out of Ethernet or out of USB or wherever. And so if we can just have just a memory port on our processors, and it's a low latency local memory port, and then from there the memory buffer they talk to has a fabric port on it, and all the I/O out to the rest of the world goes from these double ported shared memory buffers. That's what we need for composability. And then we're truly memory centric, and we're energy centric as well, because we increase the energy gracefully as we go further away from our processor.
Yeah, so there's an application angle to it, there's also a system angle to it, right? For example, if you have disaggregated memory, and if you don't have local memory, where's the operating system going to run? If your OS is going to be like running off some far thing, and that far memory dies or your node dies, you have a weird system recovery issue to deal with, right? So one of the ways, again, as a resilience guy, I think of everything from that point of view, right? So the moment you push memory away from the processor, I think the way you start bringing in, whatever the underlying memory technology is, you have to start thinking about, if things start going down, how do you clean up, right? And thinking about things, using some of the semantics for persistent memory is useful in that concept. Whether that memory is persistent or not is, effectively, if a node goes down and strands some memory far away, effectively that memory is there, and somebody has to go clean that up or understand that things are over there, right? So I think one is the hardware to enable connectivity and efficient data movement, which Alan, I completely agree is pivotal to actually make good use of these. But then you have to think about the whole system usage of these cases. Like, a lot of weird scenarios can happen where if they were all tightly integrated on one node, it's just one failure domain to deal with. Once you start spreading things around, one has to explicitly think about how do you operate it, and what do you do when you have scenarios which can happen when you start separating components, right?
Yeah, no, agree.
Yeah, case in point about it, if I may, is that, so interleaving of memory would be an interesting design to think about in terms of fault tolerance, right? Or taking out the CXL modules on the fly, right? If you interleave across multiple fabric-attached memory modules, let's say in CXL, then what is going to happen with interleaving, right? So there was a recent paper that was report rather that was published by Microsoft and and the Microsoft Research and Azure folks, where they were saying that specifically because of the fault tolerance concerns and being able to repurpose the memory, they do not use interleaving on their pooled memory, like prototyping that they do. Right, so I'll probably post the link into the chat. It's an interesting paper where they prototype CXL, right? So this trade-off in between, on one hand, we want to do interleaving for memory for obvious reasons, right? But on the other hand, because of what Sudhanu was saying, fault tolerance, and also on-the-fly dynamic composability, where do we draw a line in between, interleaving versus using individual FAM nodes, right? So yeah.
Okay, so this is kind of driving into the next question, the next question, I know that there is at least two of you that might like it, which is, and then probably I have to share my screen if I want to do it properly. Is the following: like we have this number of the interconnection technologies. We have OpenCAPI, CCIX, CXL, and it looks like that everything, at least for composability at the moment, is going to be CXL, right? Even in the work that I do daily, and I know Charles because we work together. CXL looks like being the main technology. My question is there a need for a hybrid solution? Or if you want, is CXL good at all levels from connecting from the CPU port down to the memory module? We have everything CXL, or do we need any other type of interconnection in between, depending on the device that we are connected, that we are attaching? Alan, probably you want to say something here.
I think the first thing to say is, if you remember, OpenCAPI, C6, and Gen Z, they all did try to get together back in 2016, 2017, and actually come out with one standard, but they came out with C6, OpenCAPI, and Gen Z. And there was arguments of focus. So I think it's worth touching on, but OpenCAPI was by IBM, was specifically a point-to-point accelerator connection, and it had a .mem as well as a .compute. And it was all about getting the lowest latency. They didn't want switches. They didn't want anything else. It was all about latency. Whereas, and this was Steve Fields, he was the chief engineer at the time, explanation to me, because I asked the question, I said, guys, you screwed this up. You've come out going your own 3 different ways. Now Intel's going to pick it up. This was way before CXL. and they're going to tell us how to do this. Then I was proven right. But Gen Z was certainly outside the box. There was no mention of cache. It was talking about zettabytes of access with these huge address spaces in tiered addressing. And C6 was trying to be all things to all men over the PCI bus, which IBM did try with previous versions of CAPI, by the way. So we saw this going on, and sure enough, Intel came along with Intel's strength in market and might and said, they're a little bit late to the party, but they put CXL together, and like everybody does, they all rally around. When Intel does something, we all just rally around. So in reality, it's just a semantics thing. CXL has become the Swiss Army knife. It's absorbed Gen Z. It's copied a lot of things from the .mem and the .cache. It's from OpenCAPI essentially. It's put the PCI back in, and so really what we're doing is these things are all have been learnings over the last decade, and CXL is bringing them all in under its one role. So it's all going to be called CXL, a bit like Ethernet. If you follow Ethernet over the last 20 years, lots of good ideas happen. They get copied by the Ethernet consortium and they call it Ethernet. So that's what's going to happen with CXL. They just bring all of the great ideas in, refine them where they weren't quite good, and it's going to be called CXL. So CXL is the answer to the question, yes. I think the missing piece of CXL right now is the near memory. It is definitely a far memory, no matter how you cut it. and every CXL diagram, you still see a local DDR memory, which is still parallel, which is so terrible on bandwidth perspectives. And it consumes huge beachfronts. DDR is not sustainable. In fact, you can see that it's disappearing with HBM and LPDDR being used by like NVIDIA on Grace in their GPUs. So I think DDR5 is only going to live behind the buffer. That's like a CXL buffer. But we have to address the near memory part of it. And that's where this one vestige is the open memory interface, which is part of OpenCAPI that I represent. And that's why I've been pushing it so hard. Is that's very complementary to CXL, it's basically an essential ingredient there, where you do have the low latency. I think that's something that CXL can absorb and will in time, but we have it today in production on Power 10. It works on Xilinx FPGAs. It's a great technology for us to pick up whilst we wait. CXL is still digesting and trying to get products out with the current implementation, with version 2, and they're talking about version 3, and the near memory piece of this is not in sight yet. So it would be really good to see that, you know, OMI be adopted and then be slowly integrated into CXL would be a nice direction. But CXL is the answer.
So Alan, a question here. So yeah, the thing about HBM, right, is that it's tightly coupled with the compute, right? So, you know, so having a standardized interface would be, I mean, HBM is standardized by JEDEC in a way, right? So what do you think, so like OMI stands on terms of, you know, supporting like those tightly coupled interfaces like HBM? And the follow-up question is, what do you think about this universal chiplet interconnect that is also kind of like maybe based on the CXL in the future, right? You know, like those, you know, the standards in which chiplets and maybe even memory can be connected by CXL protocol, maybe with a different PHY, right?
Yeah,
because obviously the latency and bandwidth issue, you know, requests are very different. Go ahead, sorry.
Yeah, good question, good question. The HBM side of things is very interesting. An interesting thing to note actually is HBM is actually about another 20 nanoseconds of additional latency if my information is proven correct. And when NVIDIA really introduced it with everybody, with Samsung, etc., it's all about the bandwidth. And when you get the bandwidth up to these levels, by the way, this is why it's like the power is huge for the communication when you're off package. And that's why they had to bring it on package to keep the power levels down. So HBM is really good. And you're hearing talk about using HBM for CPUs. But please note, why NVIDIA, the king of HBM, why didn't they put HBM on their Grace CPU, their ARM CPU? They put LPDDR5. There's a lot of good reasons. It's cheaper stacking, not as compared to the TSV. It's low power. And by the way, look at Apple integrating it into their M1 series. They got 800 gigabytes per second out of LPDDR. So yeah, there's a lot going on with this near memory. And to Charlie's point, we still need this low latency near memory. I guess the argument is, how much do you need? And is a small chunk like 80 gigabytes or a few hundred gigabytes of near memory, and then suddenly a jump in latency of several NUMA orders, you know, hundreds of nanoseconds, or when you go behind switches, maybe you're approaching a microsecond, how of an impact? I think there's that's where the research is. And again, I believe, so I believe the opportunity is OMI gives you the balance. It gives you the bandwidth close to HBM with the capacity and beyond the capacity of DDR, because it's a much better interface in terms of scaling more channels. And so that's where OMI sits nicely. And I see it personally, my view is we should have near memory should be OMI, the large capacity near memory. You could still have HBM on there maybe, or LP, but your first tier of large capacity memory that's shareable should have one port of OMI. So you've got basically a low latency multi-terabyte attached to a processor, local, like we have on AMD's latest processor today. They've got 12 channels of DDR5. They're up to 12 now. If you've seen the size of the packages, and they can configure that, I believe, for about 3 terabytes of DDR5. So there are use cases where they need this memory, but the question is, does it all need to be local? If we could attach that 3 terabytes with OMI to the processor, it would still have its local, you know, same latency, near enough the same latency, local memory up to 3 terabytes, up to 8 terabytes, in fact, potentially. And if it had another port on it, it was CXL, you could share that 8 terabytes with everybody else, just like CXL is currently advertising. That would give you the best of both worlds. So, and the final thing is, if people say CXL.mem is good enough for the low latency attach as well, I always point them to IBM and OpenCAPI. OpenCAPI was designed just to be point-to-point, no switches, no fanciness. And OpenCAPI.mem was not good enough for IBM to use OpenCAPI.mem as their local serial memory channel. They invented Open Memory Interface, which was a subset of OpenCAPI.mem, to get that latency down. There's no coherency aspects of it. It was to really bring it down, that latency down, because they needed it. And IBM do big memory systems, and they know they need this latency. So there's a hint there so
CXL.mem doesn't have coherency either.
Does it not? Oh, I didn't realize that. Thank you for that.
CXL.cache is coherency. CXL.mem, it's pretty much just loads and stores.
Okay, well, there we go. But the CXL.mem is like OpenCAPI.mem, and IBM decided to make this dedicated, strip it down even more. So I think CXL.mem needs to strip down to be a dedicated memory channel to get the efficiency. And you lose all of the other features, right? And this is where it becomes a hardware-wise, it becomes into a more of a detailed discussion, because CXL is a Swiss Army knife. It's got all of Gen Z features because it can support switches and go out the rack and all the rest of it. So by being a Swiss Army knife of features, you can't be a Swiss Army knife and be the lowest power, lowest latency, lowest footprint interface for just a memory channel. It's a matter of fact.
So the way CXL approaches that is that they try to prioritize, like CXL.cache and .mem is prioritized over .io, right? So on the PHY interface, which is PCI Express right now. So that actually gets me to another, like optics, right? And the optics PHY, right? Which may assist in scalability in the future and still, having latency as good as it can get in our world with the physics, right? So then what do you think about, changing PHYs, right? Not necessarily the protocols of PHYs, right? From electrical, right? PCI Express like to maybe optical or maybe something else.
Yeah, that's a logical next step, right? Is the bandwidth. We're struggling now even to get the bandwidths off of the package. And so the on-package silicon photonics is obviously the promise here. I think there might be a stepping stone. It would be nice to have pluggable silicon photonics, because silicon photonics brings ultra low power optics as well, because at the moment our optics are quite power hungry. But you've got the expense. We've been predicting silicon photonics for the last 20 years now. I guess we're getting closer. But the co-packaging, there's lots of challenges there for commercial reality. Maybe HPC will be able to afford it. But if you can couple electrically at round about a picojoule per bit, you could be more energy efficient staying electrical still in a close environment. But I think silicon photonics, if it does get to a picojoule per bit, you'll be able to do hundreds of meters with that. And so the power will make silicon photonics the obvious choice. The question will be, will the price be the obvious choice? And I think that's probably going to be the bigger issue is, can you get to the price point?
So Alan, basically to wrap up on composability, if I understand what you're proposing here is basically you're proposing of getting rid of DDR5 and having OMI. I think
the industry has already
right?
said that. I think NVIDIA have already told the industry that is the case. The reality is AMD and Intel made their latest processors with DDR5. So the train, the entire DDR5 is going to be successful because Intel and AMD have processors with DDR5 on it. But if you look at it, it's a bit yesteryear. NVIDIA have got a terabyte per second of LPDDR5. It's tremendously lower power than 12 channels of DDR5 from DIMMs going in. And capacity-wise, they've not talked, but my estimations are they're around about a terabyte, I think. Even with the LPDDR5, or maybe half a terabyte. Okay,
but from the standpoint of composability, doesn't really change the game, right? Because I don't think CXL is stepping. Sorry.
Yeah, all of these are local memories that we're talking about.
Exactly. So CXL is stepping in as is not stepping in as a local memory.
Alan is saying, I guess, is that you can replace DDR-LP, DDR-HBM with OMI, right? And OMI may be composable, or at least use. Yeah, go ahead.
Yeah, if you did it with OMI, so if you look at the power envelope as well, the power envelope of you need to decide that you want a near memory interface and like 3D, like you've got the 3D and the 2.5D of silicon. We need to go to the system level and do 3D of the system and bring the server closer together. If we can get the electrical interconnect to around about 1 to 2 picojoules per bit, that's a very efficient interface. And similar to LPDDR is 1.1 picojoules per bit on the IO at the moment. So you could get close to that on the interface. You've got the overhead of the buffer, which is, and so that does give you that little bit of overhead. But you could put DDR5 behind the buffer. You could put HBM behind the buffer. You could put LPDDR. In fact, if you put LPDDR behind the buffer, you're actually lower power than a native DDR5 DIMM, even with the OMI buffer interface. And so there's some interesting.
So Alan, I interrupt you because I wanted to like just have one last question, and then we are gonna close soon. But this was a very interesting point. So thanks, Alan, and thanks Sergey also for chiming in. So the last one is mostly, and not a curiosity, but something that we've been hitting, but it's not happening. So probably this is something that Paul probably can comment on, which is the following. So we've been seeing like many blog post announcements like run HPC on the cloud, run the HPC workloads on the cloud, and so on and so forth. But is composability perhaps a tool that can actually make peace between having different infrastructures and help creating one single infrastructure that you can just reconfigure on a need basis and have any workload running on the same system? Or do you think you will still need those very specialized, huge machines with network and so on and so forth for running an HPC workload?
So I think it can help this composability, but there are the issues of performance that we spoke about, and the applications are very very different, and I think there's a lot of technical challenges to deal with, including the aspect of authentication. So this is something that works in very different ways between HPC and cloud, and also the way that the systems are accessed in terms of the cloud models as sort of pay as you go, and sort of you pay for the access, whereas in HPC we have the peer review access to machines. So in that respect, it's also very, very different. So
with the composable system, I could cut you a system in a system, right? Mm-hmm. So take a system, cut you like a system that you can use as an HPC. So it boils down, at least naively, boils down like to the hardware.
I guess if we can deal with the issues of overhead that were mentioned before, then perhaps so. I guess I'm looking more from an HPC point of view. I don't have such a strong knowledge of cloud systems.
Yeah, and another problem is what Paul is saying, absolutely true of HPC. Another problem there is that ripple effects, right? So with HPC, unlike with cloud, you have one giant job, maybe on tens of thousands of nodes, and it's not so much even overhead on each single node from the containerization or whatever, virtualization or what have you, that related to composability. You will need some software stack for that, but it's also the ripple effects across the nodes, right? Like one tiny ripple can propagate across tens of thousands of nodes and will cause just detriment, like really big detriment to the job's performance, right? So that's another thing, like consistency, right, across multiple nodes for the composable technology is something that the cloud hyperscalers may not care about that much, because it's distributed workload and largely independent workloads that may share the infrastructure. But here it's like one large job and it needs to be in lockstep fashion, right? And so that's from the hardware perspective and software, that's going to be a big challenge.
That's right. Yes, this consistency of performance is very, very important.
I think an interesting thing as well is domain-specific architectures. I mean, that's the opposite of composability. If you look at the ON package, everyone's putting heterogeneous chiplets together and they're like physically fixed for a particular application. I'd like to be able to do that. So back to this hardware modularity, if you can actually build a domain-specific, so can we be physically composable? I mean, we've been talking about all very software dynamically composable, but I think to the point of HPC specifically, that are very big one-off applications that you run, you really want to be pretty domain specific. And you want to hardwire these accelerators together for your HPC applications. You don't want a bunch of switches burning power and latency in the way. So if you look at Summit and Frontier machines, they're hyper-converged nodes. They're homogeneous from a node perspective in terms of scaling, but they're heterogeneous. They're domain specific by their specific mix of GPUs and FPGAs and CPUs, etc. And so I think we need this balance of physical composability and dynamic composability. It'd be lovely to configure a Summit node just with this full-on composability, like a liquid approach, but maybe you discover your needs by monitoring the data flows of the communication with a dynamic software composable, and then you could physically build and get rid of the switches for your particular application and just in the lab in a day's effort, and suddenly you've banged up the performance 10x and the power down 10x for your particular piece of code, because you've built the physical composability of what you worked out with software composability in the first place, if that makes sense.
Yeah, and another big difference between those two also tends to be the cost, right? For HPC, the two, at least in the cloud market, you have very large scales, and driving down to sort of low, hardware costs as well as management costs is pretty key. And that can show up in other ways. So one of the ways it does show up is in resilience. For example, HPC, as Sergey mentioned, if you have bulk synchronous applications, you really don't want to take uncorrectable errors, which keeps bringing down a node, because that can cost a whole application or groups of processes to die, which is not a good thing when you're trying to make progress towards a solution in the application. Whereas in a cloud infrastructure, if a node goes down, maybe some VMs are taken down, or maybe you can move the VMs off, which allows you for allowing for doing optimizations which may be more cost effective, which in an HPC setting might not be acceptable at all. So that gives you some flexibility as well. It may be the same hardware which gets used in both of them, but they may be configured differently. They may be, so there are things like that to consider as well, right?
Great. Okay, well, we are quite on time with the schedule, I would say. I would have had a few more questions, but our time is out, so we will close the panel discussion here.